Welcome to Fractional Calculus seminar. Today we have Professor Yu Yu, who received her BS at Peking University in 2008 and her PhD from Brown University in 2014. She was a postdoc fellow at Harvard University after graduation, and then she joined Lehigh University as an assistant professor of applied mathematics and was promoted to full professor in 2003. Her research lies in the area of numerical analysis and scientific computing, with recent projects focusing on non-local problems and scientific machine learning. She has received an NSF Early Career Award and an Air Force Office of Scientific Research Young Investigator Program Award. Thank you very much for joining. You may please begin your talk.
Okay, yeah, thank you so much. So firstly, I want to thank Pavan and Arran for the nice invitation and for the great prestigious opportunity of presenting this work here. Yeah, and also thank you so much, Pavan, for the nice introduction. So today I'm going to talk about our recent work of learning non-local operators from data. And here I want to first apologize that, many of the talk here, I didn't really focus that much on the fractional calculus, but because of some difficulties, I'm going to explain later. So therefore, this is more like an invitation for I know many here are experts on fractional calculus and also especially on the computational aspects. So then I hope we can join the force and try to kind of expand more in this direction. So, okay, so the research work, the focus of my group in recent years is, is trying to develop a data-driven approach for the prediction and the monitoring of physical responses. So here is an example application. What you are seeing is actually an aneurysm, which is growing inside the rabbit birdie and which might eventually lead to rupture. And in this case, the aneurysm, in aneurysm, basically the arterial wall is going to change its microstructure and the mechanical property. And then sometimes it will lead to the deterioration over time. So that leads to the aneurysm growth. And then sometimes, unfortunately, it might lead to rupture. So in this type of the problem, what we are interested in is firstly trying to predict what will be the status of the aneurysm. So that of the arterial wall. So that means maybe giving me a new and unseen loading, such as like maybe high blood pressure. Then what will be the response? What will be the deformation? Is that going to get ruptured or no? And then another part, the second part is about monitoring. So we also want to understand that what's happening behind that. So this part means we want to know what is maybe the characteristics or property of the microstructure underlying it. And then, as such, we can understand that during the aneurysm growth process, what's really happening inside the human body. Okay, so here I want to emphasize that these outcomes can be mathematically described more formally. So here we are given the data, such as from MRI or from the mechanical measurements, given as the loading F, that can be seen as the hydrodynamic loading from our blood pressure and the response. So that is the displacement U here. We might be given multiple function pairs like this. And our goal has two parts. The first part is we want to find the physical model, the constitutive law of this tissue, of the arterial tissue. So that means we are looking for some operator L. This operator L is dependent on the microstructure of the tissue behind that. And the L itself should be a nonlinear operator. And then this operator maps from the displacement to the loading. So that can be seen as the constitutive law. So that's the first part. This part can be seen as we are trying to discover a forward PDE and from the data. And then once we have that, if we are having a new and unseen loading, so that is the F here, then we can basically solve this governing PDE, this forward PDE problem to get a corresponding displacement U, right? And then this part is like a forward PDE problem. But the second part is what we call monitoring. We are interested in trying to find the microstructure and the mechanical property underlying that. So that is the AX here. So this part is we are trying to discover the hidden parameter from the indirect observations, basically the F and the U pairs. We are trying to find the A. So this part is corresponding to an inverse PDE problem. So many of us knows if the governing law and also the microstructure are both unknown, this inverse PDE problem is highly ill-posed. So therefore, the second part is even more challenging than the first part. So traditionally, how do people do that? How do people model the tissue and resolve these two challenges? Because of these two challenges, usually people try to alleviate these two challenges. So for the forward PD problem, usually people try to pick some constitutive law, like develop heuristic formulation for the constitutive law to get the LD. And then for the second part, and what often has been done is instead of to alleviate the ill-posedness in this inverse PDE problem of the heterogeneity in A, people assume that the material is homogenizable. So that means instead of assume that the microstructure material property differs for each point, they assume that it should be the same for every point. So then a heuristic PDE-based approach could be like the following. So first you collect data, so collecting the UF pairs I have mentioned before. And then secondly, trying to pick the favorite heuristic model. So here, this is what I'm showing here is the foam material model. And then based on the foam material model, we try to match the stretch and the stress curve from the data we collected, and then we try to fit the kind of the homogenizable material properties. So here, that is basically the part marked by blue. We fit like four parameters from the data. And then once we have the model, then we can, for the new and unseen loading F, we can just substitute the model. We can just substitute that into the model and then run a PDE solver trying to get the corresponding displacement U. As such, we can predict the response of the material on the new loading. So this is the heuristic approach. You can see that it doesn't suffer from the two challenges I mentioned before, but however, because it depends on the heuristic model, so it might suffer from the model misspecification. And moreover, it assumes the microstructure, basically the material property is homogenizable. It's the same everywhere. So it might also suffer from the neglect of heterogeneity. And even worse, sometimes, especially for this application, PDE is probably not enough. Why? Because it's observed from experimentalists that in the tissue remodeling process, they have been observing that the cell can actually sense the fiber orientation at a long distance. So this distance is longer than the length of the fiber. And then it's going to change the material heterogeneity also in long distance. So that means if you are trying to use a local model, like a PDE model, to capture this process, then we are not going to capture the underlying mechanism. So that means at least in this particular application, PDE is not sufficiently expressive. We need more, for example, a non-local model. So therefore, our goal here is trying to develop automated non-local model discovery from data. So I guess many people here are experts in non-local operator. So I will only give some brief introduction about what is the non-local operator we are going to focus on here and why we feel that it's a better choice than the PDE model. And then lastly, I'm going to talk about two scenarios of trying to learn this non-local operator from data. Okay, so what is the non-local operator we are interested in? Here we formulate the non-local operator in a quite generic way as the following. So here the G is an operator dependent on U, which maps from the function U to function F. So in our application, this can be seen as a non-local mechanics model like Peridynamics. So here U is the displacement, F is the loading. But in other applications, it can also be seen as can also be captured the non-local diffusion equation. So for example, U can be the velocity, F can be the residue as such. But generally speaking, the non-local operator here, it parameterizes the mapping between two functions, from function u to function f in a non-local way, meaning that the state of f is dependent on the input state of u in a neighborhood of points. So this neighborhood is it can be the whole domain, but it can often also be described as a region, so as a sphere with radius delta, which we call it the horizon. And then inside, so in this operator is actually formulated as an integral operator, and this integral operator has two parts. The first part is a kernel K. So this K characterizes the interaction between two material points, between the neighboring material points. So this K is what we usually call the kernel. When we are taking this K as singular at the origin point, then it will become a fractional kernel. And then on the other hand, the BU here, it represents the nonlinearity. So for example, depends on the magnitude of U, then how the nonlinearity is going to change. And so we know that the non-local model has advantage because it can capture many effects that traditional PDE might be hard to capture. So for example, when we are looking at the anomalous behavior of materials, of fluids, and then we can take this K as a fractional kernel, and then we can capture the subdiffusion, superdiffusion behavior. And on the other hand, in the non-local mechanics model, the non-local model can simulate the material deformation together with the material rupture. So as shown on the right-hand side, which is also usually difficult for traditional PDEs. So, but now let's maybe to understand, trying to go a little bit step further, trying to understand what does that really mean intuitively or physically, this kernel K and also the operator B we propose here. So the kernel K can be think of, so for the kernel K, we look at a simple example, the linear diffusion equation, the non-local diffusion equation. So here the K, when we are trying to take this K as a radial kernel, then it corresponds to a homogeneous material. When we are taking this K, when we are looking at a heterogeneous material of two-phase, then we can take this K as the harmonic mean of the material property. So for example, the diffusivity or Young's modulus. And then this K represents the material microstructure. And then if we take this K as dependent on the direction between X and Y, so which I denote as theta here, then this K can represent the anisotropic behavior of the material. So that's usually corresponding to a fiber reinforced material. So therefore, that means intuitively, this K characterizes the microstructure information, the material property information. So that is literally the A, basically the system state, the field we have been looking for in the inverse PDE problem. On the other hand, what about the B here? What about the BU here? So here, the BU, we can again look at the nonlinear, the linear diffusion operator. In this case, as far as the K is kind of properly scaled, then when we are taking the horizon size, the delta goes to 0. It will actually converge to a local diffusion equation. So it characterizes the linear relationship in the diffusion, in the local diffusion, in the non-local diffusion. And then if you look at the nonlinear problem, so for example, here, this is the a Peridynamics model. So in this case, we usually take this BU as the strength between the two bonds, between the two material points. So here we usually parameterize that as along the direction between these two material points. So here we write as the vector here, and then the strength of it is dependent on the stretch ratio of the bond. So you can think of this bond as a spring. So when you try to keep stretching this spring, then the stiffness of this spring is going to vary with the way, with the magnitude you stretch that. So that is captured by the omega lambda here. So lambda is the stretch ratio of the bond. So one example I show on the right is the foam type, the rubbers. So that's the so-called Black-Scholes model. So basically you can see that when the lambda is equal to 1, meaning that the spring is not stretching, we are going to have the the intensity of this loading is equal to 0. It's not kind of bearing any load. But however, if we stretching that or if we compress that, then the response is going to change nonlinearly. So that's why I say that the BU represents the nonlinearity response of the material. Okay, so heuristically, both the K part and the B part should be developed by experts. But however, here what we propose to do is maybe let's try to learn the kernel K and also the nonlinearity from data from the function pairs UI and Fi. So that as such, we can capture the nonlinear constitutive relation as well as the microstructure. And by doing so, we can solve both the inverse and the forward PDE problem we mentioned at the beginning. And here I also want to emphasize that if we try to learn a nonlocal operator, to replace the PDE model, it also has additional advantages. So the first advantage is the nonlocal model is actually it's a generally more generic family of operators. So for example, for any continuous linear map between two smooth spaces, it's guaranteed we can always find a kernel K to characterize that. But this is not always true for PDEs. And on the other hand, like we discussed before, the kernel K can embed the material heterogeneity. So by doing that, it provides interpretability of what's the underlying mechanism. It solves the inverse PDE problem. And then lastly, like the PDE, we also have the nonlocal calculus tools, such as the fractional calculus tools. And then use that, we can characterize the well-posedness of the learning problem and also the model we obtained. But on the other hand, we also know that traditionally, I mean, from the computational point of view, nonlocal model might also have some additional difficulties compared to the PDEs. So the first difficulty is on the boundary condition. So generally, the nonlocal boundary condition should be, from the integration by parts, it should be provided in a region instead of in a codimensional one surface. But however, in many engineering and physical problems, actually the boundary condition should be provided like a codimensional one surface. So that makes it difficult. But however, I want to emphasize that in the data-driven approach, this issue is alleviated because the boundary region, the kind of the non-zero volume region can be provided by measurements, by data. And on the other hand, generally, the nonlocal operator, when we evaluate that, we need to calculate integral for each of the points. That could be computationally expensive. But when we are using machine learning, or for example, like a GPU training, this problem, I wouldn't say it's fully solved, but can also be alleviated because we can use GPUs to accelerate the evaluation. Okay, so hopefully I gave you some idea about why we want to develop a nonlocal operator learning approach. So now let's try to see mathematically how does that look like and what are the potential challenge. So in the first scenario we look at is learning a nonlocal constitutive law for one specimen. So basically we give like one specimen. So for example, like one tissue. This is a tissue from the heart valve of a pig, and then we are trying to use the nonlocal operator to replace the second step of the traditional PDE-based approach. That means instead of giving a heuristic PDE and also trying to assume the material is homogenizable, we try to learn the operator G by learning the kernel K and the operator B as a surrogate model. And then once we got that, we can also use that to replace the PDE in step 3 to solve for the response of the material. So mathematically, this is the procedure. Basically, we assume that we are given a bunch of the data. So that is multiple function, n numbers of function pairs of UI, that is the displacement, and the loading, Fi. And then we perform the training. So for the training, we try to minimize the operator error from the left-hand side to the right-hand side. And then we are trying to optimize the K and the B, which give us the minimized operator error. And then for the outcome to evaluate our learning effect, there are two parts. The first part is for new and unseen loading. So that is the F test here. And we are going to evaluate if the operator we learned is going to give us a small operator residue here. So that can be seen as an evaluation of the performance of the forward PDE part. And the second part is generally more challenging. So in the case that we have a ground truth kernel, we also want to evaluate if the kernel we learned, which is in an unsupervised way, does that match the ground truth kernel? So this part can be seen as we are trying to evaluate the performance of our learning as in an inverse PDE problem. So now let's try to see the performance. So here we try to collect data from a manufactured fractional kernel, and but this fractional kernel we make it flattened near the origin point. Why we are doing that, I'm going to explain later. So then in this case we are looking at a one-dimensional problem. So basically the dimension D is equal to 1, and the fractional order is 0.5. And then we are also assume that we know that we are looking at a diffusion problem. So the only purpose is trying to learn the kernel K. So then based on that, we prepare 100 numbers of function pairs by taking the ground truth U as sine, cosine functions of different frequency and also different magnitudes. And then based on this U, we use our high fidelity evaluator, like the integral evaluation, to calculate the corresponding F, the loading F. And then we use these data pairs to perform our learning by minimizing the operator error as we listed before. So then in the implementation, we just use a Riemann sum to approximate the integral. So then as such, the learning problem can be formulated as below. And what we are trying to minimize with respect to is the parameter Cm with respect to the kernel K. So here for simplicity, we can simply take the collocation points of K as the value of Cm. So learning a pointwise value of K. So, okay, so here is the performance. So if we are looking at, so firstly we try to take a final and a final mesh in this optimization based problem. Basically, we take the delta X from 0.5 to 0.0125. And firstly, on the left-hand side, on the left plot, we can see the ground truth kernel is the black one, and then the kernel we learned is getting closer and closer to the ground truth visually. On the right-hand side, on the right two plots, we evaluate the operator error on the data set, as well as the kernel error. So here we can see that the operator error, we have a second order convergence, and for the kernel error, we have roughly first order convergence. So now it looks like we have the first order convergence of the kernel. So maybe so far so good. We should all, does that mean we should all jump in to maybe use such a generic approach to learn the non-local operator? Maybe not yet. So firstly, let's understand why we get a first order convergence here. What are we really observing? So the way to see that is we can further reformulate the discretized optimization based learning as the optimization with respect to the pointwise value of K. Here I denote here, I represent that as the vector C here. And then the A is basically the coefficient matrix multiplying to the K, to the kernel value. So then that's dependent on the data of the UI here. And then the right-hand side, so basically the loading will be also formulated as a long vector. So here I represent that as F. So now what you see, this is actually a quadratic problem with respect to C, right? So AC minus F. We know the I mean the analytical solution of it. So that should be A transpose A inverse A transpose F. Assume that A transpose A is invertible. So, okay, so far so good. And then how do we understand the first order convergence? Well, if we are trying to estimate the error of the Riemann sum, we have a previous result that as far as the fractional kernel is not so singular. So for example, the S here, as far as it's smaller than D, no larger than D, then the Riemann sum is going to give us an approximation error of the integral operator in the order of delta x, first order convergence, and pointwisely. So that means in this case, if we substitute the ground truth kernel in, we should have the ground truth kernel is going to give us the residue in the order of delta x. So now we can substitute this ground truth kernel in, and we are going to get the C minus C true will be O delta x, right? So by this procedure, it looks so far so good, right? We kind of show, theoretically, we can also show there is a first order convergence, and that's what we really observed. But here I want to remind you guys, there's actually multiple pitfalls here. So what are the pitfalls? So the first pitfall is, firstly, in this procedure, when we are trying to write out the kind of the analytical formulation of C and also trying to develop the following error estimate, we have been assuming that the condition number of A is good. Firstly, A transpose A is invertible. And secondly, it should have a relatively good condition number. That means the condition number is not deteriorate with respect to the refinement of the grid. But this is not true. What we have been observing is the condition number of A transpose A is actually getting larger and larger as you refine the mesh. So that means eventually it's going to destroy the convergence. And moreover, on the other hand, in real evaluation, in here, we also assume that the U and F we prepare actually clean data. There's no noise, but this will never be true in realistic. In realistic, the data will always has noise. So therefore, here, this is not a realistic assumption yet. And the last possible pitfall is here in the Riemann sum, the error estimate, we assume that the singularity, basically the S here, is actually not too strong. So, but however, in many cases, the singularity, especially in the fractional PDE problems, the singularity will be stronger. So that means the S will be actually larger than D. So therefore, in this type of the problem, the Riemann sum error estimator is going to fail. So it no longer holds. Okay, so yeah, in this three type of the pitfalls, I'm probably going to focus a little bit more on the issue 1 and issue 2. But but for the problem number 3, we are also very interested in that, and I will be happy to discuss with you guys individually, like what is the corresponding challenge of that in the machine learning problem. So for the first two problems, let's try to see if we consider noisy data, if we consider, like say, a different. Basically a small grid and a small data of A, what will happen? So firstly, let's consider noisy data. So here we add additional, after we generate the UF pairs, we add additional noise into F. So here we basically the noise to signal ratio is equal to 1. We can see that from the operator wise, it still doesn't look from the kernel, visually it doesn't look too bad, but if you try to measure the operator error and the kernel error, we can see that the error deteriorates. It doesn't converge anymore as we refine the mesh. So therefore, this kind of the vanilla approach will fail when we have the noisy data. And secondly, what about the condition number? So here the condition number, besides the small grids, there's another way to understand this. Here I emphasize that A is dependent on the data U, right? So if I, for example, take the data U as a constant function, so U is equal to C, and then I'm always going to have a UI Y minus UIJ will be equal, UI Y minus UIX will be always equal to 0, meaning that A is 0. It's an all 0 matrix. A transpose A will also be 0. Is that invertible? Of course not. So that means here, when we consider the condition number of A, it depends on the grids. It also depends on the quality of your data. So for example, if we look at a small data problem, even without noise, but we only have two function pairs, UI and FI. Let's try to see the performance. Again, here we see that it no longer converge as we refine the mesh. The kernel deteriorates. So yeah, so then how can we try to so based on bearing these two challenges, how can we resolve it in our simple kernel learning problem? So the first thing we want to point out is in our previous analysis, we focus on vector learning framework, right? Basically, we consider discretized formulation and C is actually a vector. But however, this is not a good way to provide analysis for this problem because the A is going to change for for different grid size. So that means we don't have a consistent estimator of the A transpose A inverse. So as we have been talking about before, the condition number is actually increased. We need better way to characterize it. So therefore, the first step we do is reformulate that instead of vector learning to a function learning problem. So instead of a quadratic formulation with respect to the parameter of k, we reformulate that as a quadratic formulation with respect to the function k itself. So now here the LG, it can be seen as a continuous version of the A transpose A, but it has consistency when we try to refine the mesh because we are trying to learning that as a function. And that's the first step. And the second step, traditionally, I think maybe many of you guys also know about the machine learning, like statistical learning. When I have large noise, when I have like bad data, what should I do? People should use regularizers, right? So here we also add a regularizer. So that is the lambda R here. Lambda is the regularization parameter, which is usually tunable, and R is the regularizer. I mean, it's usually like different norms and with respect to the kernel K or the parameter of K, and then that is usually can be dependent on the problem. So then now if we substituting everything in, we can rewrite our optimization problem as the following. So now we still have the LGK true, so that's corresponding to the A transpose A, C true here. And then we still have the arrow that is introduced by the noise together with the discretization arrow. And then the inverse part, we have not only the A transpose A part, but also the part that is corresponding to the regularizer. So now let's try to see if this traditional kind of the regularized approach, does that work? So here we consider two types of the classical regularization. So that's the Tikhonov regularizer in the small L2 norm, meaning that is the vector L2 norm of the parameter C. And then it can also be the function L2 norm. So that is the function L2 that is basically the L2 norm of the function K itself. And now again, we're trying to refine our mesh from the right to the left. And here the orange line shows the operator arrow, and then the blue line shows the kernel arrow. So here we can see that again we only have two data, two measurements, two UF pairs. So now we can see that the result is slightly better. At least for the operator arrow, we do have some convergence. But still, for the kernel arrow, especially in the case that with noise, as I highlighted as the red circle here, we still is going to deteriorate as time goes on. So why is this happening? We try to understand that from the identifiability analysis. So basically, what we have been finding is actually the function space of identifiability, meaning that is the largest subspace of L2 where the kernel is the unique minimizer of the loss functional we wrote above, is actually not the full L2 space. It's actually a representing kernel Hilbert space with a reproducing kernel as the following. So looking at this reproducing kernel, we might notice one thing. So this reproducing kernel, firstly, we can see that it's a continuous version of that our A transpose A, and moreover, it's dependent on the data. So it's dependent on the U here. So that explains why that the quality of U is so important, right? When we are having only two functions, the performance deteriorates. So that's the first part. And then the second part is, so this first part means we have to learn in the space that is defined by this reproducing kernel. So intuitively, that means we should learn in the space that the ATA is actually, so basically the ATA is covered. We can never expect to have a good learning in the null space of A transpose A. And the second part is, even if we are learning in our good space, even if we not learning in the space of the null space of A transpose A, still we might have some challenge when we characterize that as a function learning problem. Why? Because the operator LG is actually a compact operator. So compact operator means the eigenvalue of that will eventually converge to 0. So therefore, that explains that why when we refine the mesh, we see a worse and worse condition number with respect to A transpose A. So yeah, so that means it's necessary to perform some operations to make it a good learning problem. So this two theory analysis is actually telling us the following. So firstly, the learning should be taking place not in the general L2, but in the right space, in the function space of identifiability. And the second part is, even in the function space of identifiability, as you refine the mesh, the inverse problem is become more and more ill-posed. So that's why the convergence, to see the convergence in the small mesh, small data, and also the noisy region is so difficult. So, but now, based on our analysis, what we propose to do is to use the RKHS norm, so basically a norm corresponding to this reproducing kernel as our regularizer. And then finally, here is our results. So to learn that from this norm is corresponding to that we are enforcing the learning in our function space of identifiability. So then as such, we are guaranteed that we are learning in the good space. So then in this problem, finally, we can see that we can have both the convergence of the estimator, so basically the kernel, together with the loss, even when the data is noisy. So, okay, so far what we have been seeing is a linear problem. So basically here what we have been trying to show is even for the linear problem, mathematically that's a very interesting problem. It's not easy because of the ill-posedness of the learning problem itself. And but now let's try to see that. Yeah, so now let's try to see that what about the performance in a real world application in a nonlinear problem. So here what we are trying to look at is a tissue data. So basically we collect the real digital image correlation data from a heart valve leaflet of a pig, and we collect like about 3,000 numbers of displacement of the corresponding to different loading of these hooks applying on the 4 sides of this tissue. And then we are trying to, so then we know that this type of material should be highly anisotropic and also highly heterogeneous and nonlinear. So, and then based on that, we are trying to write out operator G, and which depends on both the kernel. So here the kernel, I write that as M. So it depends on different angles of the, it actually depends on not only the distance between two material points, but also depends on the angle of that to represent the anisotropic property. And moreover, we also try to learn the nonlinearity that is represented by the phi here. So that captures the nonlinear response when we try to stretch the tissue. So for this model, what we are trying to do is we try to minimize the data loss with respect to our measurements, and then we try to learn both the kernel and also the nonlinear relationship, and together with the material heterogeneity. So basically, at each of the points, the fiber might have different orientations. So we learn all these three together by minimizing the data loss, and also simultaneously trying to match the stretch ratio that we are applying on the two sides of the material, and then together with some regularization on our trainable parameters. So here is the results. Firstly, we have measured the material heterogeneity, so in the form of the fiber orientation. And then this is the material heterogeneity we discovered on the second figure. So we can see that I wouldn't say they are perfect, but they are visually have some consistency. So why they are not perfect? Maybe one of the possible explanation is the measurement also has some measurement errors. So that could actually change create the discrepancy between the observation and our discovered material heterogeneity. And on the other hand, we compare the operator error. So here in the form of a test error, meaning that we train the model in 100 samples, and we try to test that in the rest of 2,000 samples. And then what we found is the classical model, they are going to have around classical PDE model has around 20% of the error. But by considering a non-local model, even without considering the material heterogeneity, we can already reduce this error by half. And even better, if we consider material heterogeneity by learning the fiber orientation, then we can further reduce that by another half. So hopefully this emphasizes the advantage of our non-local, of learning a non-local model from data. And moreover, we can also compare them. From the model, once we have the model, we can also generate the estimate of the stress field of it. So for example, here we are showing the stress field for the heterogeneous model compared to a homogeneous model. We can see that the heterogeneous model, it can highlight the high stress field at some certain material points. So these points could be the potential trigger of the material deterioration. So that could give us better explanation about the mechanism of aneurysm growth. Okay, so far this is the first part. So the first part I've been talking about trying to learn from one specimen, trying to learn the material model, the non-local model in the form of a kernel, and or in the form of a kernel together with the nonlinearity. And I've been showing that basically the learning from just learning the kernel, it already has some mathematical challenge, but this can be resolved by trying to learn in the right space, in the function space of the identifiability. And then as such, the model can also perform well in our real world applications. So now at the second part, I'm also going to, at the second part, I'm going to trying to show that in the first part, we are only focused on one specimen, so basically one tissue. But however, in real world, this is not true, right? The tissue is going to degrade, is going to deteriorate. The microstructure, the mechanical property is going to change. So a more severe question is, how can we update that? How can we capture this change? So that means if we go back to our learning framework, before we are trying to collect UF pairs, right? And we are learning only one K, only one microstructure K. So this K is dependent on the material points X and Y, and it characterizes the microstructure of this specimen. So, but however, now the question is, when we have the material property is deteriorating, the material property is changing, how can we handle multiple material properties, multiple specimens, when the microstructure change, when the mechanical property change? Can we handle that? So to do that, we use we get inspiration from ChatGPT. So why is that? So I don't know how many of you guys have been interested in ChatGPT and trying to learn the backbone of it. The backbone of ChatGPT is so-called the attention mechanism. Attention mechanism works like the following. So for example, if I have two sentences, the bank of the river and the money in the bank, in this case, I never need to tell ChatGPT that the first bank is a natural bank. Second bank is a financial bank. ChatGPT will be able to infer this context from the input automatically. How does that work? Well, it works like the following. It takes the input, so basically the sentence as an input long vector x, and then it's going to multiply this x with two trainable matrix. So then as such, it forms a matrix, what would be called the Corey matrix Q and the key matrix K. And then this is going to take the correlation between the Corey matrix and the key matrix, like word wisely. So for example, here, when we take the correlation between the words of the first sentence, the words that has the largest similarity, the largest correlation is going to have a larger score. So for example, bank is going to have the largest correlation with itself and no correlation with off and some correlation with river. So then as such, it gets the so-called attention matrix. So then the attention matrix characterizes the correlation. Then the last step is going to multiply the correlation matrix, the attention matrix with the input itself. And then together with another trainable matrix, which we call the value matrix, and get output. So in our two sentences, how does that work? The first correlation matrix, the first attention matrix in the first sentence is going multiplying with the original word is going to get out as the bank now contains 90% of bank and 10% of river. In the second case, the bank now contains 80% of bank and 20% of river. So as such, we can see that the context is actually infused into the output in the bank. So that's how ChatGPT captures the context here. So now, maybe some of you guys already realized that this procedure is actually non-local. So why? Let's try to reformulate that as a function-to-function mapping problem and see, why it's non-local. So firstly, the input function in our case, if we go back to here, our input function is the BU here. Our output function is the F. Let's substitute in, see what we get. So here we can formulate the BU as each of the measurement points as one token. And then at each token, we provide D numbers of function pairs. That is our measurement, UIFI pairs. So therefore, it becomes N numbers of tokens. And then for each token, we have a vector feature of size D. And then for the output, that is the F, we formulate in a similar way. Now we substitute everything into our attention mechanism. Let's see how does it look like. So basically, we have the Corey, we have the key, and then we have the attention matrix, and then we are going to multiply with the value matrix as such. But what we notice here is we actually have a double integral with respect to the token. So that now is our measurement, our grid points. So that's xk and xj here. When we see the double integral, since we talked about Riemann sum before, so when we see the double summation, since we talked about the Riemann sum before, a summation with respect to the grid points can be seen as a Riemann sum, right? So therefore, when we take more and more measurement points, more and more token into the continuous limit, we can rewrite this double summation as a double integral. So now let's compare with our previous model. We again have an integral of something with respect to B here, but different from what we have been seeing before of the kxy here. Now our kernel K is actually another integral. And this integral is, more importantly, is dependent on the input data, U. So therefore, the attention mechanism is also a non-local operator, and more importantly, it's actually an input-dependent kernel non-local operator. So bearing this idea in mind, let's try to combine the attention mechanism with the non-local operator learning framework we have developed. So this time, we assume that we have p numbers of microstructures. Basically, our tissue, it can be think of as the deterioration of our tissue at different weeks. So, and then for each of the microstructure A, we collect D numbers of function pairs. So then based on that, our goal is trying to learn an attention mechanism. So still trying to learn the kernel K at different time instance. And then as such, we can have a non-local operator, but with an input-dependent kernel, which can vary with time. So we still can formulate our input and output as the concatenate that as n numbers of tokens, d numbers of functions. But however, differs from the vanilla attention mechanism, we made the following. The key innovations. The first innovation is in the original attention mechanism, it only puts the information about the BU here, about the U itself. But however, in our operator learning problem, like our constitutive law learning problem, this is probably not enough, right? Because we are going to have different U, and because when we are having a different loading, it's possibly that we are, even with respect to the same U, the same displacement, dependent on different kernel K, different microstructure, we might have different loading F. So therefore, the U and F together defines the kernel, defines the K. So therefore, instead, we propose to put both U and F into the input. So the kernel should depend on both U and F. And moreover, we have, like we learned the kernel from multiple function pairs. So here we also put multiple functions as the input. And then because we have the information about both U and F, we also have the cross attention between them. So not only the self attention, but also the cross attention. And then lastly, we go through, and then when we have the input comes in, we go through L numbers of iterative layers, try to mix the information about U and F, these multiple function pairs. And then in the last layer, we are going to go through, collect the data from the else layer, and then finally get our output kernel. So that is the K here. And then computational-wise, we also do a very similar thing as what we have seen before. But for the training and the test. But the only difference here is for the training, we not only have the data from one kernel, we have multiple kernels. So here is one example. Our synthetic data is again developed from a non-local diffusion equation. But however, this time we have 7 numbers of different kernels corresponding to different decay rate. And then based on that, for each of that, we develop 2 function pairs. So that is the challenge case we have been seeing before of U and F. And then based on that, we try to perform our training by minimizing the kernel error, the operator error. But this time, the kernel is parameterized with our attention mechanism. And then for the test, we test that on a new and unseen kernel. So that means the decay rate is different. So we test both for the in distribution, that means still belongs to this family of the kernel, or auto distribution. So that is another kernel which is not inside this family. And again, we measure the operator error and also the kernel error to characterize the learning performance. Let's try to see how it works. Maybe I'm going to go a little bit fast to some of the steps. So here, what we are seeing is, firstly, we compare our operator. So now with the vanilla attention mechanism, so which I write as the discrete now, or the attention mechanism with the self-attention only. And then here I want to emphasize that the ground truth kernel we develop has a high degree of freedom, 880, but we only provide 3.2 numbers of the data, of the measurement points. So that means this is a highly ill-posed problem. The A transpose A will definitely be non-invertible, corresponding to what we talked about before for each of the specimen. But this time, because we learn from multiple kernels, so let's see the performance. So here, what we can see is the operator arrow only both the vanilla attention and our operator can perform pretty well, right? But all the other formulations, such as the self-attention only, is not sufficient to capture this change of the kernel underlying that. But however, if you try to measure the kernel error, we can see that only our approach learns the kernel error. Well, why is that? Let's try to plot out the kernel. So here, the black one is still the ground truth, and the red one is this is from the vanilla attention, and the blue line and the green line are from our null. So what we can see here is our null can actually learn the kernel pretty well, but the red one is highly oscillatory because of the non-identifiability issue that I've been seeing before. So here I also want to emphasize that we didn't use any regularizer here. So that means the attention mechanism is actually learns an identifiable kernel by itself. It addresses the ill-posedness issue we have been talking about before automatically. So, and the similar thing happens for the auto-distribution kernel. For the auto-distribution, it becomes more severe. Both operator arrow and the kernel arrow, only our approach can capture that. Maybe I'm going to go fast to go to the analysis because of the issue of time. So, yeah, okay. So, yeah, so then here we come to so why is this happening? We try to perform analysis to understand how the attention mechanism work. So remember before, if you try to learn from one specimen, one kernel, we need a regularizer to guarantee the learning is inside the function space of identifiability, right? And also the function space of identifiability is characterized by this quadratic form with respect to U. But why this time we didn't do anything? We still have good identifiability. What we try to do is we expand the attention mechanism in the non-local kernel learning as following. So here, if you try to observe how this expansion looks like, we again have a quadratic form with respect to U, right? For both the self-attention and the cross-attention. So actually, if you try to take this WQK as, like, say, a diagonal, like a diagonal matrix, and then if we are taking basically the W self and the W cross as the weights, then we can see that the kernel should belong to the function space of identifiability. So that means the attention mechanism is actually formulated as this shallow layer attention mechanism can be seen as formulating the learning inside the function space of identifiability automatically. So that's why it doesn't need any additional features to guarantee it learns in the right space. It features better identifiability. Okay, I think I'm going to jump the rest of slides and maybe it goes to the end. So yeah, so in this second part, we talk about trying to learn a foundation model which can automatically captures the change of the microstructure through an input-dependent kernel. And moreover, it features a better identifiability through exploring the right space automatically. Okay, I think I'm going to stop here. And thank you for your attention and the patience. So please let me know any question, comments will be highly appreciated. Thank you. Yeah, and also, for example, if you are interested in playing with the code, especially the attention mechanism one, you can find on my GitHub listed here.
Thank you very much, you. That was actually a very nice talk. So so for questions, please raise your hand. I'll call your name as in the order they appear in my screen. Okay, I don't really quite see any raised hand. I have a couple of questions, and I was
Please.
yeah. First of all, Yeah, first of all, I was actually very happy to see how you played with the attention mechanism. I thought that beyond language models, they may not really have real applications, but I was actually quite uh, surprised and happy to see the attention part. But I'll start before coming to the attention part. Let me start by asking the question from the first part of your talk.
Yeah,
So
yeah, please.
in the first part of your talk, you're learning you're learning the kernel, and for learning the kernel, are you expressing the kernel as some form of power series with some coefficients, or uh,
Yeah, that's a great question. So basically, so here I didn't emphasize that, but actually we try different approaches. So uh, so basically we have been trying to express the kernel simply as a neural network. So
okay?
yeah, parameterize that as a neural network. That's one approach. And we have been also trying to parameterize the kernel as the basically the using a B-spline basis. And in some of our other papers, we have been also trying to parameterize the kernel K as the Bernstein polynomial. So I would say it
Mhm.
depends on your purpose. So for example, if you feel that you want to impose some continuity of the kernel, so maybe you can
Mhm.
use neural network to enforce that. And then if you want to impose the positivity of the kernel because of maybe you want the model to be well posed. Here, I
Mhm.
didn't emphasize that part because of the limit of time, but we also have some work along that line. If you want to make sure your model you learn is automatically well posed, then you can use the Bernstein polynomial to make sure the kernel
Yeah.
is always positive as such.
Yeah, I think I'm acquainted that piece of work because I think I saw your previous talk while I was at Brown. Uh, uh, yeah, so what is that A transpose A?
Yeah,
Oh,
yeah,
I,
yeah, that's a great question. So basically the A transpose A is the U part here. So,
okay.
yeah. So basically, if you try to write what we seen above as a decomposition,
Hmm.
basically as a linear transformation with respect to K, right? Then we are going to have the A transpose A will be actually equivalent to, maybe I can try to annotate here. So then the A transpose A will come from the U here. So for example, here we can write it as K delta X, right? And then maybe K like
Hmm.
the delta, yeah, K delta here. So this is a long vector, right? And
Hmm.
then the left-hand side, we have UX1 plus delta X minus UX1. And there's another delta X here.
I see.
And then, yeah, so then the matrix
I
forms
see.
like, yeah, this part is
Yeah,
A. Yeah, this is C.
I see what you mean. I generally do it in the other way around. Uh,
I
uh,
see.
I see. So
I see.
basically, what I do, I have a long vector of views, and then in the matrix in that square matrix, I have values for the for the kernels at every point, sampled at every point. So my C, your C is basically my U. I write C, U of x1,
Yeah.
U of x2, and so I do it the other way around, but that's okay.
Yeah, yeah,
Uh,
because I guess your context is solving for U, right? So when we write out the stiffness matrix, I think the C part should be the U here. But here, because our context is trying to learn the K, so that's why the C part is actually the K, the kernel K.
No, in some cases I actually do inverse modeling as well. So, but I know the form of the my cases are mostly fractional orders, but
I see.
learning fractional orders. So TensorFlow can actually do that, but yeah, but yes, I mean computationally it becomes a bit minimizing the loss function can actually become a problem. But I think if you do it in this way. It's much better, I guess,
Yeah,
if
but
you're
still,
for inverse modeling.
yeah, but here you see that I flatten my
Yeah.
kernel. Why I'm doing that? Because the Riemann sum or any, like say, a quadrature rule, universal quadrature rule with respect to different like singularity.
Hmm.
I don't know, is there any universal quadrature rule like that can handle any singularity? So therefore, I
Yeah.
choose to flatten that. Yeah, but yeah, so So, but however, if I have a stronger singularity, if I cannot flatten that, then this might be problematic because the Riemann sum no longer give us a good approximation, and we might need to use different quadrature rule. So like different weights here for different s. Then this is no longer such a nice quadratic problem. It will be nonlinear dependent on s. So yeah,
Yeah,
that
yeah,
creates.
yeah. Yeah, I feel I feel your problem because I stumbled upon the same recently, because then I was computing singular integrals, and Gauss quadrature for sure is not the most appropriate part, because the first step of the Gauss quadrature is to take the integrand and divide it by some polynomial. If the integrand
Yeah.
itself is singular, then this never converges, but people still do it by removing the singular part, but that's not the right way to do it. So I
Yeah, yeah,
so
yeah, right. Yeah.
yeah, so I had that thought, and I was like, if I find some notes somewhere I forgot, then what idea I had. And
Mhm.
secondly, I figured out a better way of computing singular integrals, but again those thing that quadrature formula is very specific to a particular type of power law singularity. So
Yeah,
so
right, right, right. Yeah,
but
yeah,
if you
yeah.
give me any general say singular, then I'll have issue with convergence, convergence. But
Mhm, mhm.
I mean, in theory, it's fine as n goes to infinity, but we never go to infinity.
Yeah, 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 yeah. I see, I see, I see.
Yeah.
Yeah, yeah. I think that's why I was hoping that I can receive some comments and suggestion from, I mean, experts like you here who knows PDE
No,
better.
yeah.
Like, how do I resolve this issue?
Yeah, if I find, I'll go through my notes, and a part of the work is actually in my unpublished paper, and I'm waiting for my boss to approve it to put it in archive.
I
So
see, I see, I see.
so
Okay,
uh,
cool. Yeah.
so I'm waiting the moment my boss approves it and I put it in, so I can actually make it public. So I can send you that part, the other part as well, and I'll see my notes if I can actually find, if the idea that I had merit, or the other one is better. But in any case, if I find it, I'll send it to you.
Okay,
I
okay.
mean,
Yeah, that would be
if it
fantastic. Yeah,
works.
thanks a lot. Yeah, yeah.
Yeah,
Thanks.
yeah. Secondly, now learning in your second case, you had like a kernel and a nonlinear operator. Now, this is not something I have seen before, or uh, I tried to dare to learn a nonlinear operator. So
Mhm.
my question is like, first of all, what is this form of this nonlinear operator? Like, are you again using some polynomial function to construct the non-linearity? Like, let's say if you have a non-linear operator, you take some Fourier transform, then you have a convolution. So then you take that convolution as a discrete sum. Is that what you are doing?
No, no, this time we use neural network. We wanna, yeah. So this one we are not trying to like the problem before, trying to characterize, like say the convergence issue. So we simply use a neural network for both the phi and the m here. So this one, the purpose is trying to see that if our model, non-local model, can beat the traditional PDE based model. So therefore, we want to use the neural network to represent the kernel and also the B here. So then as
Mhm.
such, we can have a universal approximator.
I see. So basically, B is the output of the neural network,
Yeah,
uh,
right, right, right. Yeah, and dependent on lambda. So basically the stretch ratio
lambda.
I talked about before. Yeah.
I see. But then, how would you know that that's actually a nonlinear operator, or a nonlinear function, nonlinear function, as opposed to as a because I mean, it can happen that it is linear as well,
Mm,
because you do not know this information a priori.
I know what you mean. So, firstly, we know this material is nonlinear because
Hmm.
tissue is nonlinear. And moreover, when we are trying to, and actually here I didn't plot out the kind of the more data. Maybe some can be seen here. So you see here, we can actually have basically the loading we are applying, and we can also plot out the corresponding response, basically the displacement magnitude. I mean, on the top of this loading. So from there, we can also see the material is actually nonlinear. So basically, if they are linear, right, then they should be linearly dependent with each other. But what we have been seeing is the displacement field and the loading, they are not linearly dependent with each other. So that's another way to observe from the data that you should look for a nonlinear model.
I see, I see. So the reason you call it non-linear is from because you already know the physics, and since you have a very generic formulation, I mean, linear becomes a subcase of non-linear.
Yeah, right. So, yeah, because basically I model the BU here. So actually, maybe let me go back to here. So maybe here it can explain better. So here you see, I model the BU as the omega lambda, right? The lambda is basically the stretch ratio. So then this lambda is described as a neural network. So if we try to plot it out, we can easily see it's linear or nonlinear, but this lambda can capture the nonlinearity. This omega lambda capture the nonlinearity.
Lambda is a number, right?
Yeah, lambda is lambda is a number which get from data. Yeah.
So you take the mean of what you have on the right hand side, or mean or something, max or mean, whatever, because.
So this case, I still don't have the supervision of omega. So here, still what I'm doing is integral of k omega y minus x, and dy minus fx. And then basically I try to take an integral of this square with respect to dx. So this is what I'm trying to minimize. So I'm trying to minimize the parameter with respect to k and the parameter with respect to the omega, right? So both k and omega, they are neural networks. So that means they can capture, theoretically, they are a universal approximator to any, continuous functions.
I see. So this should also lead you to a problem of non-uniqueness, right? Because
you are right. You are totally right. So
yeah.
So that's why in this problem I didn't talk about the identifiability, because we still don't know how to have the unique approximator of this yet. This is still under investigation.
Yeah, I had this question in turbulence because as an inverse model, we wanted to see if there could be a general kernel that could actually, have this. But I never did that project because I couldn't figure it out, the uniqueness. So if you look into the paper where I have the tempered fractional, so if you change the parameter alpha, and so if you fix lambda, you can you can find an alpha. If you make lambda to lambda 1, you have alpha to alpha 2. So this is with the same right hand side, so this itself is non-unique.
Yeah, I see. Yeah, I think what we try to do is we try to impose the integral of k. So basically we try to make sure the integral of k is kind of like a fixed value, like a fixed constant. That's one way we apply. In this way, actually empirically we did observe the convergence of both k and the omega, but mathematically we don't know how to prove that. So therefore here I didn't say anything about that yet. But empirically this could be one way to impose the identifiability, to make this identifiable.
I see.
Yeah,
But this is
you see the issue is, right?
Yeah.
So basically here, if I multiply a constant to c, divide the constant to omega, then the equation doesn't change. So that's why I need to specify a constant for the integral of k to fix this constant. And then there is identifiability issue.
I see. I get your point. But then this raises another question. How do you justify the integral of the kernel equal to some constant?
Yeah,
Physically justify. That's
Yeah,
another
that's a great
question.
question. Yeah, that's a
Yeah,
great question. I mean, to be honest, we don't know the answer. We are doing this just to make it identifiable.
yeah, yeah,
So,
yeah, yeah.
yeah, I don't have a good answer for this yet.
Yeah, yes, yes. I feel you. I feel you. So hence, I'm still sticking to the more classical fractional operators than looking
Yeah.
into more general kernels because really I don't really know mathematically or physically a good enough reason to constrain something like how why would I choose this kernel opposed to another kernel?
Yeah, that's a good question. I think
Yeah,
maybe
uniqueness is an issue of inverse. Sorry.
yeah, maybe one possible way is you can say you can. I mean, that's just my guess because you have something like a non-local diffusion problem. In this
Mhm.
case, you might impose something like this, right? The integral of second moment, it should be matching something. So because this one is, I mean, how the way we match the local diffusion coefficient.
Now the issue with this is that if the kernel, let's say, is arbitrary, and let's say if it's more like a variable order, and if it has two parameters, uh,
Mhm,
two parameters, that then this becomes a non-unique problem. So
mhm, mhm,
let me just plug in k equal to the fractional kernel
mhm, mhm,
multiplied by e to exponential of minus of lambda. If I have alpha and lambda to learn at the same time, then
mhm, mhm, mhm,
this leads to non-uniqueness.
mhm, mhm, mhm. Yeah.
So
Mm, I think
more
here,
conditions, we need more conditions to impose to.
yeah, I think here maybe we don't need to worry about the lambda gets entangled here because the lambda, you
Hmm.
see, the lambda depends on you. The lambda is formulated by you, but the k is actually not formulated by, it's not dependent
Hmm.
on you. So maybe this is another way to understand this. If we are looking at basically a linear u, like a bunch of the linear displacement. So in this case, we are going to have u is equal to lambda x, right? And then we substituting. And then in this case, we can try to substituting in, then the lambda will actually be, or the original lambda might depend on x and y, but this case, lambda will just be independent of x and y. So in this case, we can take this omega part out. And then the learning problem becomes the omega lambda times the integral of kxy. You see what I mean? And then y
Yeah,
minus. Yeah, this case, you can see that it's possible to, I mean, as far as the coefficient, these two parts are separable. So
yeah.
therefore, as far as the coefficient of k is fixed, then we should have the two parts maybe more likely to be identifiable. Let's say it this way.
Yeah. But it's like posing some additional condition on omega. Uh,
It's not additional
yeah.
condition of omega. It's like if I have sufficient data from you, so then I have, like say, more observations of different lambdas, how it should behave. Then basically if I add more u, then that will help me on the learning of lambda. But it has, I mean, but it can be seen as a separable learning problem with respect to k.
Okay, let me think over it.
Yeah,
Probably.
we are still working on this. I will
Mhm.
send you the preprint once we put that on the archive too.
Sure. That would be very nice. So you mentioned a very nice point again, condition number, because that numerical methods people we are once concerned about. So how did you solve that problem of condition numbers?
So basically, we cannot solve that because this condition number issue, you see, if I have small grid, small data, then this condition number is bad, period. So, but
Hmm.
how, so therefore, the right way to solve that is to use a correct regularizer. So,
Hmm.
yeah, so basically that means in the regions that when the A transpose A is actually have a null space or close to the null space of A transpose A, then we need some regularizer applying on this subspace. So
Hmm.
that's how the idea of the RKHS regularizer is developed. So intuitively, this means we are trying to put regularizer in the path. We are trying to make sure that the paths that is in the null space of A transpose A, or the, like say, bad condition number of the A transpose A, the path that have very, very small eigenvalue, we should have that learning part. We should get 0. And we only try to learn about the other parts.
I see. So it's more of okay. And this is the paper, right? I
Yeah,
get the
this
high
is
level idea of high level idea, but I look into the formalism within
okay.
the paper,
Please,
that
please. Yeah,
paper.
thank you. Yeah, I think this one, like we are trying to formulate the learning problem and instead of a vector learning to the function learning. So then we can have consistency across different discretizations. But however, in the backbone of that, you can also understand that as the A transpose A problem.
I see. I see. I see. I see. So let's move on to the attention part because that's the new bit. With I would say I'm not sure anybody even thought about like using attention as this. So it's I have to admit that it's been a long time looking into the attention part because I was doing something on language modeling, but
Oh,
uh, yeah, I mean, not as work. I was doing an assignment for my course.
I see. But that's
Nothing fancy.
but it is so exciting that you're also working on the language model. Yeah,
No,
that's
no, I'm not.
interesting.
No, no, I'm not working. It was a part of my deep learning course at Brown.
Oh,
So I was
oh,
doing that.
really? Really?
Yeah.
Oh, that's interesting. I see. That's super interesting. Yeah.
Or maybe I read paper somewhere. So it was okay. Okay, my boundaries over there between research and studies were a bit ambiguous. So I don't remember why did I read that paper, but yeah, uh, maybe okay. So on the implementation level,
Mhm.
you still have a fully connected neural network, and the output of the new of the neural network, one of the output of the neural network is the values of the matrix of the attentions, the right.
No,
How
I
do you
think the
plan?
implementation that it's actually a different neural network architecture.
I
So
see.
intuitively, it's like this. So you have, I mean, the input vector, something look like this, right? So then it multiplies with a pointwise, like the
Mhm.
matrix WQ, basically the Q here. And then that is basically the query I have been listing before. And then it's going to take a dot product with also the same thing, but then it's take a pointwise multiplication with the K. So that is the key matrix. And then
Mhm.
these two guys, they are going to take a correlation. So basically the
Ah,
correlation
I
means
see, I
you're
see.
trying to do, yeah, each pair you are trying to do a dot product. And then this will become the attention matrix. So you see that's a different architecture of
Different
neural.
architecture. Hmm.
Yeah.
Hmm. Okay. And so how do you learn a kernel from this technique? So that was the part that I'm a little lost, and I'm also interested in this. So how do you learn a kernel?
Yeah. So basically I formulate the attention mechanism output as a kernel.
Ah, I see,
So
I see.
So you see, that's corresponding to here.
Mhm.
This is our kernel. So this guy is our kernel. Of course, I add some additional layers. I add a cross attention, but intuitively, this is the kernel we are looking for. So that's another advantage of this attention
Mm,
mechanism. It's
I see,
interpretable. It naturally has a kernel in that already.
I see.
So then you see the rest is very similar to our kernel learning problem because I mean this kernel is unsupervised. So we just do the integral of kernel and then b
Mm,
buy dy minus f. You try to minimize this error.
minimize
That's
this.
very, very similar to our kernel learning problem.
But the kernel comes from this attention mechanism.
Right. That's the only difference. And the kernel is dependent on the input based on the attention mechanism.
Yeah. That's actually quite brilliant. Brilliant idea. I mean, I never thought that. I would implement attention in such a manner. That's that's actually pretty nice. I'll have to actually read up my previous notes as well because I forgot all the details of this architecture.
I
Channel.
see.
But is your paper online or you're still
Yeah,
working?
it's on archive. It's accepted in NeuroIPS as a spotlight paper already. So it's already,
Okay, okay,
yeah.
okay. So it's one of the neural IPS paper. Okay, so I'll look into that paper as well, and if I have further questions, so I'll 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 ask you. But I get the high level idea.
Yeah, please. Yeah, I think this is
Quite
actually
the high
really,
level idea.
really yeah, this is also a new direction that I mean very interested in because you see that we have a new
Mm,
value that finding our non-local operator is so important. And
mm,
moreover, I think our non-local analysis also possibly will give the tool for us to understand the attention mechanism. So now there's very little mathematical work on the understanding of attention mechanism, but our non-local calculus, non-local analysis could be a
mm,
potential.
mm. Okay, since you mentioned about non-local calculus, let me also mention this if you are not acquainted with regards to arbitrary kernels. There is a work by Professor Luchko.
Okay.
He also has some mathematical formalism of having a derivative like operator and an integral operator where the kernel satisfy the zoning condition.
Oh,
Uh,
that's interesting. Yeah. So maybe
there
can
is
you?
some formalism yeah, I can send you. I can send you.
Yeah,
I
yeah,
send,
please,
send you.
please, please. That sounds super interesting. Yeah, thank you. Yeah, and
Yeah.
also if you know any work that has like say maybe some maybe quadrature rule or mesh free formulation or maybe any discretization approach that can cross maybe can handle the singularity. I mean without like knowing
Yeah.
the singularity in the ones. Please also can you also share that with me? I think that's literally what we are looking for too.
On that part, I personally developed all those techniques, and because in the literature I quite didn't like what they were doing,
I
so
see, I see, I see. Oh,
so I
great,
had
great. Okay.
so I
Yeah.
had my own way of computing computing convolutions and quadrature techniques which could be the idea is actually very simple, but my boss is not uh, uh, hasn't approved it yet, and he's
I see.
traveling yet.
Oh,
So
I see, I see, I see. Oh, so that's the
and
paper you are referring to. Yeah. So if possible, I mean, I would appreciate if you can share that with me later. And maybe if you're interested in this topic, we can even work on that together.
Yeah, sure. We can figure something out. And on more of that discretization technique. So I developed this spectral method for that for discretizing general fractional operators.
Oh, amazing.
Which is where the kernel is arbitrary. The idea is that with the right kind of basis function,
Mhm.
the convolution is
Mhm, mhm.
equal to a simple function. So I call them as Jacobi convolution polynomials.
I
Uh,
see, I see. So
uh,
super interesting.
so when you take when you write an approximation of like f equal to uh,
Mhm.
uh, the sum of some coefficients time the Jacobi convolution, and then you plug into the general fractional operator where you have instead of plug as f and the property is that it will be the sum of the coefficients times uh, uh, the Jacobi polynomial, and then you test it, that then we know the orthogonality as well. So you have spectral convergence in that sense, but I'm still awaiting.
I see, I see. That sounds super interesting. Yeah. I would definitely love to learn more. Yeah.
Yeah,
Yeah.
sure. So once he approves it, I'll send it to you. Send it to
Yeah.
you.
Yeah. Thank you so much. That will be super helpful. Thank you.
Thank you. Yeah, it's my pleasure. Pleasure.
Yeah, no. Thank you. Yeah, I think that's literally the kind of the missing part, the missing piece we are looking for to extend this to fractional kernel.
Sure. So let me okay. Let's do this. If I find that paper, I'll send you over that paper, and then we can discuss if there is something to be done.
Yeah, that sounds fantastic. Yeah, thank you.
Okay. So that's pretty much all. Okay. Yeah. Okay. That's pretty much all the questions from my side. But let me ask if there are some people in the audience, if they have any question or remark, you can unmute your mic.
Yeah, or if you have any question, you can also send it to my email. Oh, yeah. So, and any question, comments will be highly appreciated.
All right. So I'm assuming right now there are no further questions. So this is a good point to close this talk.
Yeah.
Thank you again for the nice talk. It was very much enjoyable.
Yeah, thank you so much, Pavan, for the kind words and also for the kind opportunity. I think I learned a lot from the discussion.
Yeah, it's a pleasure on my side. Thank you.
Okay, yeah, it's